Okay, so we're starting chapter 3. Now remember, as we go through these videos, you can always pause and try a problem yourself, and then fast forward to the end and see if you got it right. You can always pause if you need to take a break. You should rewind if you've missed something or something was unclear, and you can always watch these videos more than once. Today we're going to be looking at the real numbers and different types of number systems and absolute value. We're reviewing that a little bit and using the graphing calculator. So make sure you have your graphing calculator nearby. So first we want to look at our definitions for rational numbers, irrational numbers, and the real numbers. So the rational numbers are any number that can be written as a fraction a over b, when b does not equal 0. Remember, our denominator cannot be 0. So 3/4 is a rational number. 2 is a rational number because I could put it over 1 if I wanted to. 1.3 is a rational number because it's 1 3/10 or 13/10 if I wanted to write it as a fraction. Repeating decimals are rational because they can be expressed as a fraction. Negative numbers are rational as long as they can be expressed as a fraction. So rational numbers come in all sorts of shapes and sizes. Even a mixed number like 1 4/5 can be expressed as a fraction a over b. So that is rational. And the key word in rational is ratio. Next we have the irrational numbers. And those are numbers that have infinite decimal parts that don't repeat. We sometimes call them nit nerds. That stands for non-terminating, non-repeating, decimals. Non-terminating, non-repeating decimals. So irrationals are numbers like the square root of 3. If you put that in your calculator, you'll see you'll get a decimal that is not repeating and it doesn't end. Pi is a pretty famous irrational number. Square root of 7. I could give you a decimal that has a pattern. 1 0 1 0 0 1 0 0 0. So there's a clear pattern there, but it is not a repeating pattern over and over. So those are the irrationals. And then together, they make up the real numbers. The real numbers are all the rationals and all the irrationals. So that's really the big set. The biggest set of numbers that you know are the real numbers. Every real number that you know can be graphed on a number line. So I would suggest right now that you pause this video and try and place these 6 values on this number line. Maybe putting 0 in the middle to give you a place to start. So pause the video and put all these decimals on the number line. Okay. So this is how I see all of these numbers placed. You could have converted them all to decimals if you needed to compare, and that might be a good way to check if you got any of them wrong. All right. Let's review graphing inequalities. We did a little bit of it in the first chapter, and I'm going to introduce what's called interval notation as well. So here, and here. So first let's get these graphed on the number lines. We have the conjunctive inequality. -2 is less than, x is less than or equal to 5. So we know here we're open on -2, closed on 5, and that the x values are between these two numbers. In interval notation, we put an open parenthesis on -2, and we know we're going to 5, and we put a square bracket on 5. The parenthesis means exclusive, not including, and the square bracket means inclusive, including. So I'm including 5, I am not including -2. Let's take a look at the next one. X is less than 4. We know open on 4, shading to the left for less than. Or x is greater than 10, open on 10, shading to the right for greater than. So this interval notation is a little bit different because it's disjunctive, it's disjointed. So we're going to have two parts. And what I'm going to have to consider going to the left is that I'm going to -infinity. And moving to the right in this direction forever means that I'm going to +infinity. So reading this from the left to the right, if I just, go along this answer here, reading it from the left to the right, I have open on -infinity all the way to 4, open. And then we're going to put a union there, and that shows you that it was an OR question, an OR inequality. So -infinity to 4, I've got that section. And I got to travel all the way over to here, and now I need to express this section. So open or including 10. Open on 10, and the infinities always get a parenthesis. So that one's done. How is this next one different? Well, the only way I see is that instead of just less than, I have less than equal to, and instead of just greater than, I have greater than equal to. So I'm going to shade in and to the left from 4, shade in and to the right from 10. Remember again, that means I'm going to infinity. And if I'm moving left, I'm going to -infinity. The only difference between these two are that I'm including those values 4 and 10. So -infinity to 4, square bracket, union, 10 to infinity. So we want to encourage you to use these interval notations whenever you can to express your inequalities, and you definitely will see them again. So don't be shy to give them a try. Let me move this out of the way and let's go on. Quick review of the absolute value inequalities and equation. Remember, we're going to split once our bars are alone. So here x equals 5, and on the right hand side x equals -5. So this equation is simply the points -5, a point, and 5, a point. And those are our solutions. Absolute value bars are alone, split, x is less than 5, and x is flip, and negate. Put your values in, and let's figure out which way we're shading. We've got that our x's are less than 5. That's going to the left of 5. And our x's are greater than -5. Greater than -5, going to the right. And we are open on these two because it doesn't include. So this solution set has as answers -5 is less than x is less than 5. There we go. Conjunctive inequality. And the last one, absolute value bars are alone. X is greater than 5. And on the right, x is flip and negate. Let me throw down our numbers here. They're the same in every case. We're just showing you the differences in the shading. X is greater than 5. From 5 going bigger. X is less than -5. From -5 going lower. So one way to write this inequality is with right up here with the ors in the middle. Let me just circle that. Up here I could have put an and in the middle and circled that. But now we have another way to express these as well. When we have inequalities, we can write them in interval notation. So working from this one, I could have -infinity to -5, parentheses or bracket, union 5 to infinity. So there's another way to express that answer. And here, with the and example, I would have everything between -5 and 5, not including them. Okay, and these are just points. These are nothing like an inequality. They're a little simpler. So let's try a tougher problem here. A few tougher problems here. Recalling the steps, the bars need to be alone. They are. Split. 3a minus 5 is greater than 4. 3a minus 5. Flip. Negate. Okay, you may want to pause and see if you get this one right. So on a number line here, these are squeezed in pretty tight. On a number line, I've got a 1/3 and I've got a 3 to deal with. It says my a's are less than 1/3, less than goes to the left. My a's are greater than 3, greater goes to the right, greater in that direction. Obviously I have a disjunctive. We're going to write it like that. Or our new notation with our awesome infinities. -infinity to 1/3, not including soft parentheses. 3 to infinity. Hope you got that one right. You should be able to write these. Write these solutions for all of these. Let's do this second example here. Remember, we have to get the bars alone. So right now, I'm not ready to go. I'm going to add 4 to both sides. 3 with the bars. Is less than or equal to 9. Still not ready to go. I need to divide by 3. So what I have now is the absolute value of 2x plus 2 is less than or equal to 3. Now I'm ready to split and go on. On the left, 2x plus 2 less than or equal to 3. And on the right, the exact same thing, but flip your inequality and negate the 3. Don't negate anything else, just the 3. Let's work this out. I'm squeezing things in, so I'm going to maybe skip a couple steps, subtract 2, divide by 2, x is less than or equal to 1/2. And on the right-hand side, I'd be subtracting 2 and dividing by 2. And it looks like, I'll do a number line. Squeeze that in maybe over here. You use your number line to help you figure out if you're doing a between or an away. Do they go away from these two numbers, or is it between? So I see my x is less than or equal to 1/2, solid dot going to the left. And my x is greater than or equal to -5/2, solid dot going to the right. So we have a conjunctive inequality. We can write this with an and. We can write this by throwing in our x in the middle. Since they're shaded in the middle of these, the x goes in the middle. And I can write this in interval notation. Why do I have hard brackets this time? Because it's also equal to these values. All right, last part here. I'm going to skip example 3. We can do it in class if you'd like to. It is a toughie. It's got a negative in it, so it has a bunch more steps. But I'd like to get to the graphing problem now and do a little, have a little discussion on solving absolute value problems when they're, by graphing. I'm sorry, I'm getting tongue-tied. So this would be, let me grab a different color. This would be a strategy if I had the problem absolute value of 2x minus 1 equals 3. Nice. Neaten that up. So what you're able to do is you're able to grab the left-hand side of an equation and put it into y1. We're going to do that in just a second. And grab the right-hand side of an equation and put it into y2. And then what we can do, where would two graphs be equal to each other? And they would be equal to each other where they intersect. And then we can talk about our less than and greater than and all of that stuff. So let's say we're looking for the equation first. So let's grab your graphing calculator, and we're going to put into our y equals. I'm going to clear out what's there. And I want the absolute value of 2x minus 1. So math, num, and absolute value is your first choice. Okay? 2x. Minus 1. Good, that's our left-hand side. And then our right-hand side goes in y2. And we're good. We're ready to graph these. And actually this little graph here in the middle, you see it done for you. Let's hit a zoom 6, zoom standard window. And there's our absolute value graph, and here comes the y equals 3. So to figure out where they're equal to each other, I'm going to clear this history so you can see what I do now. To figure out where they're equal to each other, I'm going to go to second, trace, and I'm going to choose number 5, which says intersect. And it'll tell me where my graphs intersect. So second, trace, intersect. Now the prompt at the bottom of your screen says, is this the first curve? And you can see you just move your arrows a little bit, your flasher is on that absolute value curve. So that, yes, that is our first curve. So hit enter. Then the prompt in the bottom left corner says, is this your second curve? You can move it around if you want, but I can tell it's on the line, and that was our second curve. So the answer is yes, just hit enter to accept. So now it's saying guess. Well, remember we were trying to figure out where they intersected. So I'm going to come back to real close where the intersection is. Look at my screen where the flasher is. It's right about there. But I don't have to guess. The calculator will tell me as soon as I hit enter. So look what I have. -1, 3. Remember that value. -1, 3. Matter of fact, I will come back to this in a sec. I know that one of my answers for x is -1. Remember, we're just solving for x. Back to the graph. I'm going to go find that other intersection. Okay, the steps are on there. I'll do them again. Second, trace, intersect. We know that the absolute value, we know the curves are right. Second curve, first curve, those are all correct. The only thing we need to change is to get closer to, get your flasher closer to the other intersection. Just closer to it. And hit enter to get your calculator to tell you that that point is the point 2, 3. Remember, we only need the x value, so the x value is 2. So we just did this graphically. We found where the equations were equal. If we did it by hand, we would get these same answers. Let's take a minute and graph on your little grid here. X-axis, y-axis, never forget to label. Always label. And I'm going to graph the curve 2x minus 1, and I'm going to graph the curve 3. And I'll do them both in blue. Now 3 is very easy, so here it comes. Okay. If you need help with the graph of y equals 2x minus 1, you can use the table on your graphing calculator. As long as its table set is set up nice, starting at 0, counting by 1s. Looks good? Second table. And you can see your table. It's in my middle screen here and on my calculator screen. So those are some of the points that I'm going to graph for my absolute value curve. I see -2, 5, -1, 3. Okay. So -2, 5, -1, 3. I have the point 0, 1, and the point 1, 1, and then 2, 3, and 3, 5. Now remember, absolute value graphs, you saw the picture of it. Absolute value graphs come down and make a V. So this little section down here where these are leveled off means that it meets right in the middle down there on that axis. Let me see if I can get some decent lines here. All right, they're not perfect. Kind of in the shadows here. So this was the graph of y equals the absolute value of 2x minus 1. And we could circle our intersections. X is negative 1 and x is 2. Well, the last thing I want to do with you, because using a calculator can be really powerful, is talk about what if we were solving 2x minus 1 is less than 3. Same graph for y1, same graph for y2. What does the less than mean is the big question. So if we look at the picture, we are asking, where is the absolute value graph, what, compared to 3? And less than means you can look under the line of 3. So if I look under the line of 3, then we're dealing with this section right here. This section has x's that go from negative 1 to positive 2. So it's a conjunctive inequality. And there's our solution set for that. I'll skip an interval notation for a second while I let that sink in. Less than means I'm going to be looking under. Okay. What if I asked the question, where is my absolute value graph greater than 3? Greater should be disjunctive. So I'm asking where the absolute value graph is what compared to 3? Greater than 3. How about above the 3 line? So let's go look at our graph again, which we're really making very messy. And where is it above the 3 line? Where is the absolute value graph above the 3 line? Well, from here this way, and from here this way. Whoops, that kind of got crazy. And where do those x's go? Well, on this side they go from negative 1 that way forever. And on this side they go from 2 that way forever. These lines are misbehaving. Sorry about that. We'll just get rid of them. So for the greater than solution set, this section is represented by all of our x's are less than negative 1. And the other green section is represented by all of our x's are greater than 2. And as we said before, it's disjunctive. So we can do these algebraically, and they're typically pretty easy to do algebraically, but we can also do them graphically. And that's going to be a very powerful tool for you to use all year. See you tomorrow.